So now let us start with the first mode of heat transfer, which is conduction. Conduction is in fact the transfer of energy from the more energetic particles to less energetic particles as a result of interaction between the particles. So you can see over here that the definition says that the energy will be transferred from more energetic particles to less energetic particles as a result of interaction between the molecules or atoms or particles. Now, what does this mean? It means that when one particle would come in contact with the other particle, the energy would be transferred. Conduction can take place in solids, liquids as well as gases. So some people think that it only takes place in solids, which is not true. In fact, conduction can take place in all three modes, in all three forms: solids, liquids as well as gases. Now let's start with how does conduction take place in gases. You know that the gas molecules are farther apart, and the solid molecules are very close to each other due to the attractive forces between the atoms or molecules. Now, if we consider the conduction in gases first, and if we think of if we consider a snooker table, right, and consider all those balls as molecules. So what we do over here is that we use the red ball to hit we use the white ball rather to hit the colored balls. So when the white ball is moving with a certain velocity, and when it hits, for example, a red ball, so what happens is that the white ball either stops or it decelerates, and the ball and the red ball which would be hit by the white ball would start moving. Now it is almost the same principle which is applied in the case of conduction in gases. This is very simple. All that happens is that the higher energetic molecules would be hitting the lower energetic molecules, and when they would hit the lower energetic molecules, a part of energy would be transferred from the higher energetic particles to the less energetic particles. This is what is meant by interaction between the particles. Now, coming back, now what happens in solids, because gases is one extreme and the solids is the other extreme, the liquids is in between the two. Now what happens in solids is that in solids the conduction process phenomena takes place due to the definition says due to the combination of vibration of the molecules in a lattice structure and the energy transport via free electrons. Now, as you know that the solid molecules are not free to roam around, just like the gas molecules. The gas molecules move here and there freely, whereas solid molecules do not move here and there freely. Rather, they vibrate about their mean position. Right. So, consider. I would give you an example over here. Consider, for example, this figure, in which there are molecules arranged in here, right? So let's say we are heating up the first end, right? So the molecules over this end will get heated up, and since they are vibrating, so their amplitude of vibration will increase, right? And then they will hit the second molecule or the second line of molecules. So a part of energy will be transferred to the second line of molecules. So when the second line of molecules would get that energy as a result of that interaction, they will start vibrating with with more amplitude, higher amplitude, and then they will hit the third line of molecules, the third set of molecules. And upon this interaction, a part of energy will be transferred from the second set of molecules to the third set of molecules, and this is how the energy will be transferred from second to third to fourth, and then so on up till the other end. So this is what is meant by. So this is what will happen in the case of solids. Right? That it will be due to the vibrational motion of the molecules, and which are arranged in a lattice structure. Now, in solids or in metals, there are free electrons as well, and the free electrons will also move from one end to the other, and they also contribute to the heat transfer, to the energy transfer from one end to the other. So in solids, the conduction is due to the combination of the motion of the molecules which are arranged in the lattice structure, and the energy transport by the free electrons, right? So that is why the metals conduct more energy than, for example, gases, because they have got the free electrons. This is the same thing that I have explained over there. When two molecules possessing different kinetic energies, right, collide with each other, then part of the kinetic energy of the more energetic molecule will be transferred to the less energetic or lower temperature molecule, thus moving the energy from one place to the other. This is what we use to illustrate the conduction process in gases. Now, this is the thing that I was explaining, and that in the case of solids, there would be the molecules which are arranged in this lattice structure. So they would be colliding with the first one, will collide with the second one, and then second will collide with the third one, and then fourth one, and so on. And this is how the energy will be transferred from this end to the other end. And in addition to this molecular, in addition to this energy transfer due to molecular movement, there are free electrons as well that will also contribute towards the energy transfer from one part to the other. You would have noticed that if you take a bar or a spoon and put it in fire, and so what will happen is that this end will first start getting heated up, right? And after a few minutes, you will feel that the other end will also start getting hot. Although this end is not directly facing the fire, but in fact the energy is in fact flowing from this end to the other end. And if it is a solid, if it is for example a metallic bar or a steel spoon, so not only the molecules will contribute to the energy transfer process, to the conduction process, but the free electrons will also contribute in the conduction process. So this is the illustration of conduction. This is a figure from our book, in Corpora and Divit, and it also illustrates the conduction phenomena. You may go over the details in the book. Over here it is showing that there is a plane, and when the molecules are passing this plane, so there is a possibility that the molecules, some of the molecules may not collide but pass a certain plane, and when they pass a certain plane, the energy will be on the other side of the plane. And this is what I have just covered, right? That this is the solid This is the molecular structure in case of solids, where there is a lattice structure, and due to the vibration of the molecules, the energy is transferred from one end to the other. And in the case of gases, where the molecules are free to roam about, the energy will be transferred when one molecule will collide with the other. Of course, the two phenomena, as for example in gases and in the solids, are the same. Now, the thing is that in the case of solids, it is a typical structure. It is a lattice structure between the molecules, which is missing in the case of gases. And in the case of solids, especially in metals, we have got the free electrons, which also contribute towards the energy transfer. Now, the heat conduction expression is given in the form of a law which is called the Fourier's law, and you would have gone over this expression in some previous classes, where Q is given as minus Ka delta T over L, or minus Ka delta T over delta X. Now this is the expression for the heat transfer in X direction. Like Qx means the X is in the suffix of Q, so Q is in watts, and X is indicating that the heat is being transferred in X direction. Heat may be transferred in one dimension or two dimensions or all the three dimensions, but in the beginning we are considering the heat transfer in one direction. If the heat is being transferred in one dimension only, we call it one dimension heat transfer. Similarly, 2D, two-dimensional heat transfer, and 3D or three-dimensional heat transfer. Now Q is minus Ka delta T over delta X. So Q is directly proportional to Q, the heat transfer in watts is directly proportional to delta T. Is directly proportional to delta T. And over here, if you look at the figure, this T1 is the temperature on this face. This is a wall, right? This is a wall. This is one side of the wall, right? And this is the other side of the wall. This is the other side of the wall. This, we are talking about this side, and opposite to this face of the wall, there is another face over here. You should understand what I am trying to say. Now, the temperatures over here are T1 and T2. So T1 is not the temperature at this edge. T1 is not the temperature at this edge, and T2 is not the temperature at this edge. Rather, T2 is the temperature on this whole face, right? And T1 is not the temperature on this edge. Rather, it is the temperature on this face, which is opposite to this face, right? So when the heat will flow in X direction, it will flow from one face to the other face and not from one edge to the other edge. Now, if the heat is flowing in this direction, it means that T1 would be greater than T2 because the heat flows in the negative, in the direction of the decreasing temperature. So when T1 is greater than T2, the heat will flow in this direction, the direction of the decreasing temperature, and the temperature may decrease linearly. This is the temperature distribution diagram, you can say, where T is given as a function of X. Right? So this L is in fact the thickness of the wall. If we are considering the heat flow in this direction, in X direction. Now, the temperature may vary linearly between the two faces, or it may vary non-linearly. So in subsequent chapters we would also be uh, looking at various temperatures at the expression of temperature, at the function of temperature. When we say function of temperature, we mean temperature as a function of x, temperature as a function of x, or temperature as a function of y, or temperature as a function of z. If we are considering a plane wall, if we are dealing with Cartesian coordinate system, because Cartesian coordinate system would be dealt with in x, y and z. So this L is in fact the you may call it length, but it's better to call it the thickness of the medium, because this is the thickness through which the heat has to flow, right? And it shouldn't be a surprise for you that the larger the temperature difference, the larger the difference between T1 and T2, more would be the amount of heat that will flow, right? So Q is directly proportional to the temperature difference, and Q is inversely proportional to L. Q is inversely proportional to the thickness of the medium. You may very well call this L as delta X. So Q is inversely proportional to the thickness of the medium, because the larger the thickness of the medium, the more would be the resistance offered by the medium. The more would be the resistance offered by the medium to the heat flow or to the heat flux. So heat transfer is in fact directly proportional to the temperature difference. The larger the temperature difference, more would be the heat transfer. And the heat transfer is inversely proportional to the thickness of the medium. The thicker the medium is, the lesser would be the heat transferred. And this Q is also directly proportional to A. Now this A is in fact, you may see over here, the area normal to the direction of the heat flow. It is the area normal to the direction of heat flow. For example, if heat is flowing in this direction, the area that will be normal to this heat flow would be this area, this whole face on the other side, right? So this area is not the frontal area, rather this is the area which is normal to the direction of heat flow. And this negative sign indicates that the heat is transferred from higher temperature to lower temperature. This negative sign indicates that the heat is transferred from higher temperature to lower temperature. So if we write it as T1 minus T2, instead of T2 minus T1, so that T1 or if we for example take this negative sign in there, right? So it would become T1 minus T2. So then this Q would be a positive quantity. If we take this negative sign in there, then this Q would become a negative quantity, or T2 minus T1 would be a negative quantity, because T2 is less than T1. So when this negative quantity will be multiplied with this negative sign, it would again come positive. So minus sign in fact over here is being put to indicate that the heat flows in the direction of decreasing temperature. Over here we would not be using negative Q's and positive Q's in the terms of heat supplied and heat rejected, as is done in some other cases. For example, in the case of power plant engineering, some people use heat supplied in the boiler as a positive sign, and the heat rejected in the condenser as a negative sign. But over here, if it is flowing in the positive x direction, then we would be representing this heat flow with a positive sign, and if it is flowing in the negative x direction, then Qx would be written with a negative sign. We will see it in subsequent problems and chapters. The last thing is or let's discuss this thing first. So this Q is written, may be written in this form, or it may be written as minus K delta T over delta X, or it may be written as minus K dt over dx. So this change may be written in this form, change in temperature, or this change in temperature may be written in terms of delta, or this change in temperature may be written in terms of d. Now if we are using dt by dx, it means that we have t as a function of x. If we are writing dt by dx, it means that we have t as a function of x. Just like when we write dy by dx, it means that we would be differentiating y with x. For that we need a function relating y and x. So we would be having functions of t in x. Just like over here, you can say that over here this tx would be having a form of y is equal to mx plus c, or t is equal to mx plus c, because it is a linear line. Similarly, there would be a dt by dy if we are considering the heat transfer in y direction, and there would be a dt by dz if we are considering the heat transfer in z direction. Now this is a very simple thing. You can see that if we bring this area over here, then this would become Q by A, and Q by A is in fact the heat flux. So Q would be in watts, heat flux would be in watt per square meter, and this area would be having units of square meter. This temperature difference may be in degrees Celsius or it may be in Kelvin, because the temperature difference in degrees Celsius is equal to the temperature difference in Kelvin. Because if you add 273 over here and 273 over here, both 273s would get cancelled out because of this negative sign in between the two. And this thickness of the medium, L or delta X, would again have the units of length. Now the last thing is K. This K is what we call the thermal conductivity. K is what we call the thermal conductivity. Now what is thermal conductivity? Thermal conductivity is very simply the ability of a material to conduct heat. It is the ability of a material to conduct heat. Right? So if a material is able to conduct more heat, we call it a good heat conductor or a good conductor. And if it is able to conduct less heat, so we call it a poor conductor or an insulator. Right? So thermal conductivity is simply the ability of a material to conduct heat. If we make use of this expression which we were looking at on the previous slide, that Q was Ka delta T over delta X. Over here there is a separation. Right? So this expression of K has been written with this Fourier's law. So over here K may be written as Q over A. A will go into the denominator, and then delta X would in fact come over there in the numerator, and then delta T would go into the denominator. So kindly correct this thing, this will go over here. Right? So now the thermal conductivity of a material as per this expression can be defined as the rate of heat transfer Q through a unit thickness of a material per unit area per unit temperature difference. So in fact this, if you work the units out, you will get the units of K as watt per meter per Kelvin or watt per meter degree Celsius. For example, if we go back over here, so Q is in watts, this area by L, so A by L would have the units of length. So this meter will go into the denominator of Q, and this temperature difference will also go into the denominator of Q. So K would be having units of watts per meter Celsius or watts per meter Kelvin. So it is in fact from this expression, from this formula, we can define thermal conductivity as the rate of heat transfer through a unit thickness of material per unit area per unit temperature difference. For example, the thermal conductivity of pure copper at room temperature is 401 watts per meter Kelvin. So that would mean that if we have a 1 meter thick copper wall, means if delta X is 1, if we have a 1 meter thick copper wall, it will conduct heat at a rate of 401 watts per square meter area. Per square meter area, and that area would be the area normal to the direction of heat flow per degree Celsius temperature difference across the wall. Right? This is what it means. Over here we are being shown some materials and the thermal conductivities of those materials, and if you I have used various figures in here. If you see a sort of a pinkish figure, that would be from Yunus Sinjil, and if you see an orangish figure, that would be from Incorpora and David. So over here we are being shown some conductivities of various materials. Diamond has got the highest thermal conductivity, which is 2300. By the way, all those thermal conductivities are at room temperature. In fact, the thermal conductivity varies with temperature. So after diamond, we can see that we have got the list of metals: silver, copper, gold, aluminum, iron. So all those are metals. So the solids have got the highest conductivities, and in solids metals have got the highest conductivities because they have got the free electrons. So due to the free electrons, their the ability of conducting the heat becomes much more as compared to non-metallic solids. And then we can see that glass and brick have got very low thermal conductivities. Those are solids as well, but they are non-metallic solids, 0.7. And then comes the liquid, water, and then the gases. For example, helium. For example, air is in fact an insulator because it has got a very low thermal conductivity of 0.026 watts per meter Kelvin. So as a rule of thumb, you can say that the solids have got the highest conductivities, and the conductivities of liquids are usually less than the solids, and the conductivities of the gases are the least usually. Now over here is being shown the variation of the thermal conductivities with temperature. So for example, you can see over here that the thermal, for example, let's see what we do have on the axis. On x-axis we have got the temperature. And on y-axis we have got the thermal conductivity in watts per meter Kelvin. And over here, for example, the thermal conductivity of metallic solids such as silver and copper decrease with an increase in temperature. It decreases from about 400 to about 350 or something like that. The conductivity of iron, for example, decreases by a large amount from about 120, 130 to about 30 watts per meter Kelvin. So this is in fact showing us the variation of the thermal conductivities with temperature. The thermal conductivities of materials vary over a wide range. This is what we are looking at over here. The thermal conductivity of gases is proportional to the square root of the absolute temperature. Is proportional to the square root of the absolute temperature T, and inversely proportional to the square root of the molar mass. Right? So you can go over the details of the variation of the thermal conductivities from interoperant debate. I am only highlighting a few important points. The important point is that the thermal conductivity is not a constant quantity. Rather, it varies with temperature. It varies with other parameters as well, which we will discuss later. But right now we are looking at the variation of the thermal conductivity with the temperature of the material. Unlike gases, the thermal conductivity of most liquids decrease with increasing temperature. It decreases in the increasing temperature, with water being an exception. And like gases, over here, unlike gases, the thermal conductivity of most liquids was decreasing with increasing temperature. And like gases, the conductivity of liquids decreases with increasing molar mass. A very interesting fact about the thermal conductivities is that we make an alloy consisting of 2 or 3 or n number of metals, and when we develop an alloy, we expect the properties of the alloy to be better than the properties of the metals. And it is the case, of course, for example, when we consider strength, etc. But when it comes to the thermal conductivity, the thermal conductivity of alloy would be less than the thermal conductivity of either of the metals. For example, if metal 1 has a conductivity of K1 and metal 2 has a conductivity of K2, for example, let's say that K1 is 150 and K2 is 200 watts per meter Kelvin, then the thermal conductivity of alloy would be less than both the thermal conductivities. Means it would be less than 150 and it would be less than 200. Means it would be having a value, in fact, less than 150, because again 150 is less than 200. So the thermal conductivities of alloys are less than the conductivities of the constituent metals.